Okay, let's just be honest with ourselves for a second. We are officially living in the agent era.
Oh, without a doubt.
I mean, it is late February 2026, and AI isn't just, chatting with us anymore. It's moved way past that phase.
Right. It really has shifted from being a smart chatbot to
Yeah.
being, well, kind of a junior coworker.
Yeah!
A tireless, very fast junior coworker.
Exactly. But here's the thing that keeps me up at night, and I know I'm not alone in this. If I download one of these open source agents, something that can actually manipulate files and run terminal commands.
Right. Something with hands.
Right. And I set it loose on my laptop, isn't that kind of like handing a complete stranger the keys to my house and saying, hey, go fix the plumbing, try not to break anything, and please don't look in the drawer where I keep my tax returns?
It is absolutely terrifying.
Oh.
You are giving an autonomous piece of software
Yeah.
read-write access to your file system if that agent hallucinates, or if the model behind it has been compromised, or if it's just, I don't know, decides to delete the wrong folder. The blast radius is your entire machine. Yeah. We can talk about catastrophic levels of disaster here.
Which is why today's deep dive is it's so timely. We are looking at a brand new release from Docker that dropped just a couple of days ago on February 23rd.
Right.
It's a technical guide by Oleg Selejev, and it tackles this exact fear.
It's a solution for running OpenClaw, which is this very popular open source coding agent, completely securely.
And not just securely, locally.
Right.
The promise here is massive for anyone listening. We are talking about a fully private, local AI coding setup. No cloud dependencies, no API costs. And this is the real kicker, running inside a secure sandbox that acts like a digital fortress.
Yes.
And apparently you can set this up in like 2 commands.
2-ish commands. Let's be precise. It's streamlined, but there's some nuance there.
Fair enough, 2-ish commands. So our mission today for you, the listener, is to unpack this entire setup. We're going to look at the 3 pillars that make this architecture work, the magic user experience, and then, because I know you love this part, we are going to dig into the technical plumbing.
I really do.
Specifically, a very clever, slightly messy workaround they had to invent to make the networking actually behave.
Oh, the bridge script. It is a fascinating piece of engineering. It solves a problem that has plagued developers for years regarding Node.js networking, and they applied it specifically to this AI agent context. It's a great example of do whatever you have to do to make things work.
I can't wait to get to that, but let's start with the cast of characters here. We have OpenClaw, Docker Sandboxes, and Docker Model Runner. Let's take them one by one. What exactly is OpenClaw?
OpenClaw is an open source AI coding agent. Think of it as a tool designed specifically to write software. It has a terminal UI or TUI. So imagine opening your terminal and seeing a dashboard that looks a bit like those old school hacker interfaces, or maybe HTOP if you use Linux.
So it's not a web browser thing.
No, it lives right in the terminal. You give it a task like refactor this Python script.
Yeah.
And it doesn't just suggest code. It acts. It creates files, edits them, and runs terminal commands to test its own work. It really attempts to be autonomous.
Okay, so that's the stranger I'm worried about inviting into my hard drive. That's the thing with the hands.
Precisely. OpenClaw is the engine that does the work. But normally, OpenClaw needs a brain. It needs a large language model to tell it what to do. Usually that means connecting to the cloud, sending your data to OpenAI or Anthropic.
Right. But this guide is about doing it locally, which brings us to the second pillar. Docker Sandboxes. Now, I know what a Docker container is. I use them all the time. Everyone listening probably uses them. How is a sandbox different?
This is a critical distinction, and honestly, it's the most important part for security. A standard Docker container shares the kernel of the host operating system. It's isolated, using namespaces, sure, but it's still running on the exact same kernel. If there's a kernel vulnerability, like a zero-day exploit in Linux itself, a malicious process inside that container can potentially break out.
They can escape the container and basically take over the host laptop.
Exactly. But Docker sandboxes are a new primitive in the ecosystem. They aren't just containers. They use isolated micro VMs.
A micro VM. So it's like a tiny self-contained computer running inside my computer.
That's right. It has its own kernel. It's a much harder boundary to cross. It's like the difference between locking someone in a room in your house versus locking them in a separate shed out in the backyard. Even if they break out of the room, they're still just in the shed. They aren't in your house.
I love that analogy. So the shed is the sandbox. But the feature that really matters for our discussion today is the network proxy, right?
Yes. These sandboxes come with a configurable proxy that lets you strictly control where the agent can connect. You can block it from talking to random internet hosts entirely.
So if the agent goes rogue and tries to download a virus or, say, upload my passwords to a server in a non-extradition country, the sandbox just says no.
The door's locked. It can't get out.
Yeah.
The network traffic just dies right there at the border.
That is the peace of mind I've been waiting for. Okay, third pillar. Docker Model Runner. This sounds like the brain part you mentioned earlier.
It is. The Docker Model Runner is what allows you to run the AI model, the actual intelligence, directly on your host machine. So imagine your laptop is the host. You have the model runner running there, utilizing your GPU, serving up models.
And these are local models we're talking about.
Completely local. The source mentions models like AI/GPT-OS:20B-UD-Q4_K_XL or the Qwen 2.57b model. These are powerful open weights models that run locally on your hardware. You download them once, just like a Docker image, and then they run entirely offline.
So let me just get the architecture straight before we move on. OpenClaw, the agent writing the code, is locked inside the secure sandbox, the shed in the backyard.
Yes.
The model runner, the brain, is sitting comfortably on my actual laptop inside the house.
You got it. And this separation is key. The heavy lifting of the AI inference happens on your host, where you have access to your GPU and your system resources. But the risky part, the file manipulation and command execution, happens inside the isolated sandbox.
And because it's local, I'm not paying per token.
0 API costs. You can let it loop for 6 hours trying to fix a bug, and it costs you nothing but electricity.
That is the dream. Okay, so that's the theory. Let's talk about the magic setup. The guide claims I can get this running in 2-ish commands. Walk me through the workflow. I'm sitting at my desk. I have Docker Desktop installed. What do I do?
First, you need to make sure Docker Model Runner is enabled in your settings. Once that's done, step 1 is getting the brain. You pull the model. The command is straightforward. Docker model pull, and then the model name, like A/GPTs.
Just like pulling a standard container image.
Exactly. Now you have the brain. Step 2 is creating the environment. You run Docker Sandbox, create --name OpenClaw using the pre-built image provided in the guide.
Okay, sandbox created. I have my shed in the backyard.
Now, step 3 is where we handle the security. You need to configure that network lock we talked about. By default, the sandbox is a black hole. Nothing goes in, nothing comes out. But OpenClaw needs to talk to the brain. So you run Docker Sandbox Network Proxy OpenClaw -- allow host localhost.
Let's pause on that. -- allow host localhost. Why am I allowing localhost? Doesn't that mean I'm opening it up to my computer?
You are punching a very, very specific hole in the firewall. You are saying you are allowed to talk to the host machine, your laptop, but absolutely nothing else. You aren't opening it to the broader internet, just the specific channel needed for the brain to talk to the hands.
Got it. So it's a direct line of communication, not an open door.
Exactly. And then step 4, Docker Sandbox run OpenClaw. You drop into the terminal inside the sandbox, you run the start script, which is just ~start openclaw.ish, and boom, you are staring at the OpenClaw UI.
That is incredibly slick. So I'm in this terminal chatting with the AI. I ask it to write a Python script or a React component. It writes the code to a file, but that file is inside the sandbox, right?
Correct. It's writing to the workspace inside that micro VM. If it decides to run arm-r/ and delete everything, it only deletes the files inside the sandbox. Your family photos, your tax documents, your actual project files on your laptop are completely safe.
That is the level of isolation I need to actually sleep at night. And there is always a but in these deep dives. It's never quite as simple as just connecting the wires, is it?
It rarely is. And this is where we get to the aha moment of this guide. There was a significant technical hurdle they had to overcome to make OpenClaw actually talk to the model runner.
This is the part about the networking bridge. I read this section 3 times to make sure I understood it. It involves Node.js, right?
Yes. So OpenClaw is built on Node.js, specifically Node 22. Now, here's the problem. Node.js is notorious for not respecting standard proxy environment variables by default, especially when talking to localhost.
Wait, really? So if the system says, hey, route all traffic through this proxy, Node just ignores it?
In many configurations, yes, it tries to go direct. And remember, we are inside a sandbox. If OpenClaw tries to connect to localhost, it is connecting to itself inside the sandbox. It's not connecting to your laptop where the model runner actually is.
Right. Localhost is relative. My localhost is not your localhost. So OpenClaw is shouting hello into its own empty room while the brain is sitting outside on the host machine.
Exactly. The Docker Model Runner is listening on port 12434 on the host. The sandbox has a special proxy address, usually host.docker.internal:3128, that can reach the host. But OpenClaw, being a stubborn Node app, wasn't using that proxy correctly to reach the model. It kept trying to connect directly to itself.
So they had to build a bridge.
A literal bridge script. It's a tiny, roughly 20-line Node.js script included right in the image.
How does it work? Paint the picture for me.
Okay, visualize the data flow. OpenClaw initiates a request. Instead of trying to reach the host directly, it connects to this bridge script running inside the sandbox on port 54321.
Okay, so OpenClaw calls 127.0.0.1:54321. That works because the bridge is in the same room, so to speak.
Correct. Now, the bridge accepts that request. Its only job is to take that request and explicitly forward it through the sandbox's proxy at host.docker.internal:3128.
It's like a middleman who knows the secret knock.
Yes, or a smuggler. The proxy then takes that request, passes it through the secure boundary of the micro VM, and delivers it safely to the model runner on the host at port 12434.
So the path is OpenClaw to the local bridge, to the sandbox proxy, to the host model runner.
All to circumvent the fact that Node.js acts a bit entitled regarding network settings.
That is such a classic developer solution. The standard way didn't work, so I wrote 20 lines of code to force it to work.
It perfectly illustrates the complexity of these isolated environments. You want security, you want isolation, but you also need these things to talk to each other. That bridge script is the glue holding the local AI experience together. Without it, the brain and the hands simply couldn't communicate.
Now, speaking of security, we talked about running this with local models, but the source material mentions that some people might still want to use cloud models. Maybe the local model isn't smart enough for a really complex coding task, and you want to call in the big guns like Anthropic or OpenAI.
Right, and you might think, well, if I use a cloud model, I have to give the agent my API key, right? And that brings us back to the fear of the agent leaking that key.
Right. If I paste my Anthropic API key into a config file inside the sandbox, and the agent reads that config file, couldn't it accidentally print it out or send it somewhere?
In a traditional setup, absolutely. If you put your API key in a .env file inside a container, any code running in that container can read it. It's game over if it gets out. But Docker Sandboxes handle this with something called credential injection.
Credential injection, that sounds incredibly cool. How does it work?
It's very elegant. You set your API key, say _API_keyway, as an environment variable on your host machine, your laptop. You do not put it inside the sandbox.
Okay, so the key is on my laptop outside the shed.
Correct. When OpenClaw sends a request to Anthropic's API, it sends it without a key. It sends a broken request, essentially.
So how does it actually authenticate then?
The request hits the sandbox proxy first. The proxy recognizes the destination. It says, well, this is going to Anthropic. And it stamps the API key into the header as the request leaves the secure environment.
Wait, so the agent OpenClaw never actually sees the key?
Never. The agent literally doesn't know the key exists. It just knows that its requests are magically working. The proxy handles the authentication entirely at the border.
That solves a huge supply chain security problem. I mean, we're always warned, don't put secrets in your code, don't put secrets in your containers. This actually enforces that at the infrastructure level.
Exactly. And if you're using cloud models, the security gets even tighter. You remember how we had to use the flag -- allow host, local host for the local model?
Yeah, so we could reach the model runner.
If you are using cloud models, you don't even need that. You can block local host access entirely. The only thing the agent can do is talk to the specific cloud API endpoint allowed by the proxy. It is an incredibly strict isolation level.
That allows for a really cool workflow the source mentions. You could use the free local model for testing, hey, write me a hello world, and then switch to the paid cloud model for the heavy lifting, all within the exact same sandbox.
It's the best of both worlds. You experiment for free, deploy with power, and stay secure the whole time.
I love that. It feels like a mature way to handle these tools. Okay, so we've covered the user path, the two-command setup, but our listeners are curious people. Some of them are DIY enthusiasts. The guide doesn't just give you a fish, it teaches you how to catch one. It explains how to build this image from scratch.
And this is where you see how flexible this system really is. The recipe for building this is fascinatingly simple, yet robust.
Walk us through the ingredients. If I wanted to build this myself, what am I actually doing?
You start with a base shell sandbox. That's your empty micro VM. Then you install the runtime. Specifically, they use npm install-gn and then run n22 to get node version 22.
Right, because OpenClaw needs the latest and greatest.
Then you install OpenClaw itself via npm at latest, But then comes the manual labor dash, the code injection. You literally use a cat command in the terminal to create that model runner bridge.js file we talked about earlier.
You're handcrafting the bridge right inside the box.
Exactly. You are pasting that 20 lines of code into the file system. And finally, there's a bit of config hacking. OpenClaw needs to know that this new Docker Model Runner provider exists. It's not in the default config. So the guide uses a Python script to inject a JSON snippet into OpenClaw's settings.
It's like hot wiring the agent to accept a new brain transplant.
That is a vivid way to put it, but yes.
Yeah.
The Python script merges the provider settings, defining the model name, the context window, and pointing the base URL to that local bridge at 127.0.0.1:54321.
And once you've done all that tinkering, installing Node, writing the bridge, hacking the config, you don't want to lose it when you close the sandbox.
Right, because sandboxes are ephemeral. So Docker allows you to run Docker Sandbox Save. It freezes the state of that micro VM into a reusable image. You can tag it, push it to a registry, and then anyone else can pull it and run it.
Democratizing the toolchain. I could build a specialized Java coding agent sandbox with all the right JDKs and Maven plugins, save it, and share it with my entire team.
Exactly. And they wouldn't have to do any of the setup. They just run Docker Sandbox Run. They get the security and the tools without the headache.
That is powerful. It really feels like we are moving past the Wild West phase of AI agents into something much more managed and mature.
We are taming the beast.
Yeah.
We went from a scary AI agent that might delete my hard drive to a controlled, isolated worker inside a glass box.
So let's wrap this up. We've unpacked the tech, OpenClaw for the hands, Model Runner for the brain, and Sandboxes for the secure room. We've seen the clever bridge hack to get around Node.js networking quirks and the credential injection that keeps our API keys completely safe.
And the big picture here, which is referenced in the State of Agentic AI reports, is that this is paving the way for unsupervised agents. Tools like Claude Code, Gemini, Codex, Dash. We want them to work for us while we sleep. We want to give them a task at 5 p.m. and come back to a finished pull request at 9 a.m. But we can only do that if we deeply trust the environment they run in.
Trust is the currency of automation. If I don't trust it, I have to watch it. If I have to watch it, I might as well just write the code myself.
Perfectly said. Docker Sandboxes are trying to build that infrastructure of trust. They're trying to make it safe to look away.
Now, before we go, I want to leave you, the listener, with a thought. We spent a good chunk of time talking about that 20-line bridge script, the fact that a modern runtime like Node.js essentially ignored the proxy configuration, forcing a manual workaround.
It was a necessary hack, yes, but it is concerning.
It makes me wonder, if that was necessary for something as basic as a proxy, something that is supposed to be standard across the board, what other invisible networking assumptions are our AI tools making that we aren't aware of? When we download these massive libraries and agents, what other protocols are they silently ignoring or bypassing?
That is a chilling thought. If the security controls we think are in place, like HTTP proxy variables, are being silently ignored by the runtime, are we actually as secure as we think we are? Are there other doors being left wide open because the software thinks it knows better than the infrastructure?
And what does that mean for the next generation of security exploits? Maybe the next big vulnerability isn't in the code itself, but in the silent assumptions about how that code talks to the network.
It's definitely something to chew on. The gap between configured as secure and actually secure might be wider than we think.
Something to mull over while you are running your secure, local, sandboxed AI agent. Give it a try. Pull the image, run the commands, and see what it feels like to have an AI coding for you without the fear of imminent destruction. Thanks for joining us on this deep dive. Stay curious, stay secure, and we will catch you in the next one.
Goodbye, everyone.